start the recording. Okay. So Stefan studied at the University of Hanover and the Technical University in Munich, where he completed his PhD. Following a research fellowship at the University of Milano e Laboratori Grazionali del Gran Sasso and a guest professorship at the University of Tokyo, he was appointed to lead an independent research group at the Max Planck Institute in Heidelberg. In 2010, he was appointed as the chair of the experimental particle physics at TUM, and he was a founding and long-term spokesperson of the International GERDA collaboration and European spokesperson for the International LEGEND collaboration since 2017. He is vice spokesperson of the Collaborative Research Center 1258 Neutrinos and Dark Matter, and the principal investigator of in the universe and the New Origins Cluster of Excellence, and currently Vice Dean of the Technical University Munich Physics Department. I hope I introduce you completely. So he conducted the research in the field of astroparticle physics, focusing on the investigation of the properties of the elementary neutrino particles and its role as a messenger in astroparticle physics process, and on exploration of the nature of dark matter. So today, he will lead a discussion of the quest for Majorana neutrinos with GERDA and LEGEND. Thank you very much, Stefan. Yeah. Thank you.
Thank you very much for a kind invitation, and thank you for this very nice introduction. By the way, I'm not Vice Dean anymore. I succeeded to stop that obligation, to end that.
Okay, sorry.
So, no. So I'm happy today to discuss basically the center of the research work I'm dedicating most of my time to, which is the quest for Majorana neutrinos, and to tell you about the outcomes of the Gird experiment and our planning for the LEGEND experiment, which is basically under its way. So let me start with a very simple the quest to point what is driving us, not only me, in that field. The particle properties of neutrinos are still very much unknown. We know they do have mass, and thanks to the pioneering work of Snow experiment, which then really proved that neutrinos do have mass, that flavor conversion occurs. And so this was a major breakthrough. But we still don't know anything about, well, the absolute mass scale of neutrinos, and we don't know about the ordering. And here this scheme on showing qualitatively, we know the mass splitting from oscillation experiment here from the sun, from atmospheric oscillations, and however, we don't know exactly how they are ordered, whether this is so-called normal ordering scheme, where the small splitting is basically happening between the lightest two neutrinos, so coming from the solar observations, or whether between the heavier two ones, which then would be the inverted ordering. And we don't know the absolute scale here. And this can be either hierarchical, or it can also be quasi-degenerate or quasi-degenerate, where basically the all offset is large compared to the splitting of the neutrinos. I put here also a very important question about whether there are additional sterile states, and you know that there's lots of work going into trying to understand and looking for whether the indications or hints which have been found could be basically established towards sterile neutrinos, and also for related to our neutrinos double beta decay or the lepton number violation search. Also there, they obviously have an impact in the observable later on. Nonetheless, I will basically rather stay most of the time really in the three neutrino paradigm, that we have three mixing neutrinos. But very much the question which is unanswered and which has probably the biggest impact on our understanding of neutrino particle properties, but also for question of the evolution of our universe, is basically whether neutrinos are their own antiparticles or they're distinct. And you know that lepton number violation would be very natural, and because there's no reason for any global symmetry, for this global symmetry to be exact. And you can look up here the famous article. So the question is, why are neutrinos so much lighter than charged leptons? And what is the matter and antimatter asymmetry? What is the origin of that? So, I mean, all that is intrinsically connected to the question whether neutrinos are their own antiparticles. And the way we're trying to shed light onto that is we are looking for the so-called neutrino double beta decay. And here my little illustration, which shows you look a big ensemble of nuclei, and then you wait and see suddenly two beta particles appearing. And if that occurs, and so only two beta particles and no neutrinos accompanying this process. So if that occurs, then you can talk about that this is a creation of matter without balancing emission of antimatter. And this is to quote Francesco Visani, who said we should not only call it neutrinos double beta decay, but we should call it maybe lepton. Well, he suggested why not using leptogenesis, but this already is used for other purposes. But maybe creation of matter without balancing emission of antimatter is I think, a good picture of what we're looking for. And the underlying nuclear process is that simultaneously in a nuclei, there's the transformation of two protons here into two neutrons into two protons, and the emission of two electrons, and basically no electron antineutrinos accompanying that. So in that process, you see immediately that the lepton number would be violated here by 2 units. You have 2 electrons more than before, and no antiparticles, no antileptons with that. And this process now we're looking for can basically be generated by a lot of theories beyond the standard model. So any beyond the standard model operator, which is lepton number violating by 2 units, can in principle also generate neutrinos double beta decay. However, in our simple, or let's say our paradigm of 3 light Majorana neutrinos, then this is enough to generate neutrinos double beta decay. So if you have Majorana neutrinos, that is neutrinos and antineutrinos are identical particles, then this is enough to generate neutrinos double beta decay. And as already mentioned briefly, the Majorana neutrino would explain why neutrinos are so small through the famous seesaw mechanism. And through the so-called leptogenesis method, you could also basically have a very clear scheme how the matter-antimatter asymmetry basically could occur. So this is a key ingredient. And so these 2 very fundamental questions is really very clear that this is driving us. And maybe you can summarize it that the discovery of neutrinos double beta decay would always imply new physics. So where are we now in the moment with this search? So the current best sensitivity is 10 to the 26 years and that's basically in this provided by the Gird experiment I will discuss in a moment. Its final sensitivity surpassed the 10 to the 26 years. As you know, we have not found the signal. We only could provide limits. And that's the reason why we basically were motivated to move on. And we want to, in the next generation of experiments, to increase our sensitivity by a factor of 100 to get to 10 to the 28 years. And it's clear that this is a huge challenge because what we're looking for are very rare decays. We're basically looking for 1 decay per 10 to the 4 mole a year. So, I mean, this is a very small number of events you want to discriminate. Now, let me come back here to the standard paradigm. And here on the left, you see basically here the Feynman diagram for neutrinos double beta decay. You have these 2 neutrons here inside a nucleus. And these 2 neutrons basically are decaying simultaneously here, exchanging here neutrino. And in the final state, you have here the 2 electrons. And how is that connected with the intrinsic parameters of neutrino properties. It's shown here. Here is shown the so-called effective Majorana mass, MEE or M beta beta, often used, and you see that this is can be written as the coherent sum of the eigenstates, the new eigenstates here in the first row, and so multiplied with the elements of the first row of your PMNS matrix. And you can see also that this is coherent sum because these elements can be complex. And so you can obviously have then also some cancellation, as you will see in a moment. It was really, I think, Schecht and Valle in their early paper, they said that any neutrinoless double beta decay process, so whatever, whether it's now driven by light Majorana neutrinos or by any other BSM physics, can basically induces an effective Majorana mass term. So, so that's basically then here the famous block that you just connect your outer lines, and you, whatever is happening driving here this neutrinoless double beta decay, you always basically have a transition between electron neutrino, electron antineutrino, and that is basically an effective Majorana mass term. It has also been pointed out by these authors that this number can be numerically very tiny and that other leading contributions to neutrino mass must then exist. Still, this statement that if you find neutrinos double beta decay, that this then proves that neutrinos do have Majorana character holds independently of that. So one slide that neutrinos double beta decay is not something, I mean, looking for lepton number violation is not something which only neutrinos double beta decay can do. And you know that at Gird Experiment, you can just look at this diagram and turn it around by 90 degrees. And you see, if you can look here in processes looking for dileptons of the same sign. Also, that would basically be here a neutrinos double beta decay equivalent process. And now, obviously, these are not the light Majorana neutrinos which are exchanged here, but we're talking here about the TeV scale. But also, this TeV scale particles could also obviously drive the neutrinos double beta decay. And there have been some work over the last years where people have compared basically LHC physics and double beta decay, and you can see basically how that compares here. For example, GERDA or ton scale Germanium experiment, LEGEND, basically how that compares to Collider experiment. This is just a short illustration how that there's a connection, obviously, to BSM physics or collider physics if you go beyond also your 3 light Majorana neutrinos as a leading term driving the lepton number violating process. Now, let me come back to the 2 neutrino and the 0 neutrino double beta decay and bring towards the experimental search which we're doing and the signatures we're looking for. So the 2 neutrino double beta decay here, there in the final state, you have basically here your 4 leptons, and they basically share the energy and momentum of this decay. And if you measure the sum energy of these 2 electrons here, and they basically look like a beta spectrum, obviously with more particles than just in a single beta spectrum, but it's a continuous spectrum which basically goes up to the Q value of this decay. In the 0 neutrino double beta decay, you have basically here just in the final state 2 electrons. And if you measure the sum, then they basically, the sum of them is just equivalent to the Q value of this decay. And then you see a sharp peak here, depending the sharpness on the energy resolution of your detector. So that's basically you're looking for. And now let me just put this all again together with our introduction about this effective M beta beta. What are we looking for experimentally is a decay, and we can measure decay rate. And this decay rate here basically is connected to our elementary particle properties here, this effective M beta beta here. And then you have your Nucleomatrix element to the square, and you have a phase space integral, which you can calculate very precisely. And here, just once again, our M beta beta here, this effective neutrino mass being the coherent sum. And these are complex numbers, as mentioned before, and that's why, you know, you can have also here cancellation. Just to wrap up, the experimental signature of all double beta decay experiments is you look for an energy deposition here at Q beta beta of the sum of these two electrons. These two electrons come from one vertex from where basically the decay occurs. And the discovery, as mentioned before, would imply that lepton number violation is 2 units. Neutrinos do have Majorana character. We would learn something about the mass scale, and it is clearly a clear sign for M beta beta. Now, what do we know from oscillation experiment? You know that oscillation experiments basically tell us something about the solar splitting, the atmospheric splitting. You have theta 1,2, theta 1,3 measured. However, we don't know the absolute scale, and you can write your M beta beta here or MEE just as a function of these parameters with the unknown of M1 and your CP violating Majorana phases. And I think this famous Visani plot, I call it, here's an update from a recent version of Visani and students. And you know that we expect, we plot here M beta beta as a function of the lightest neutrino mass, which M1, which as we say, we don't know, and we don't know the ordering. If we have this so-called normal ordering, then you're in this, reddish color, and you see that you come here basically down, you have some lower bounds here, which are at the 1 millielectron volt scale. And in case of the inverted ordering here, you are at the 10, 20 millielectron volt scale here as a lower bound. And here in this so-called quasi-degenerate parameter space, there's no major difference between your ordering. So, and I mentioned before that you can have basically destructive interference, and you have basic cancellation. And that's just here in this parameter space. If nature was really tuning it very finely and we are very unlucky, then you know this number can be very small, that this is experimentally absolutely not accessible. So a couple of years ago, Matteo Agostini, Giovanni Benato, and Jason Detweiler looked on the distributions and made some global Bayesian analysis, taking the oscillation parameters. They used also in single beta limits and cosmology, and said, okay, let's look what is the probability distribution of this parameter space under the assumption of some priors. For example, they said, okay, we know nothing about the Majorana phase, we just take them as flat, and for the lightest neutrino mass, they said, okay, let's assume that is scale invariant. And then they basically looked at the distribution and, for example, the probability by this, based on these priors, so if you have no fine tuning, that you have a fully cancellation, it's very small, so very little points down here. If you look at the cumulative distributions, maybe that's you look here, for example, here for the inverted ordering, you see that if you have an experiment which is here just a little bit below your 20 millielectron volt, then you have basically a sensitivity, you have a discovery sensitivity, which is basically 100%. However, very interesting also for the normal ordering, if you have an experiment here at the 10, 20 millielectron scale, then basically you get something like 50% of the parameter space, you have a discovery sensitivity. So sometimes people say if normal ordering was the right solution, then next generation of double beta decay experiment had no chance to see. That's not correct. So you have a very good chance to see. Obviously, there's no guarantee. It's not a guaranteed signal in case you have a normal ordering with the next generation of experiments. Now, the experiments which are basically being prepared now for the next generation really aim at discovery. And for the discovery, the sensitivity, it's very important to look at the backgrounds. And here, this is one plot which shows here the 3 sigma discovery level here in half-life versus the exposure of, now this is the case for germanium, but this applies obviously for any other device or isotope as well. Now, if you're background free, then you're basically here on this solid line, and you just basically increase here linearly. The moment you have some background, very little background even, so you're not anymore on this solid line, you come here to this dotted line, and just depending how much background you have to increase tremendously your exposure to get the same sensitivity. So let's just make this example. Here, this line, we have something like, we assume we have 0.1 counts per region of interest in ton here. And if I go down here to 10, so this is a big step, and you have to get here, increase your exposure by that number. And you see that's very insane. It's very, I mean, you should really always work on your background, reduce your background such that you're as close as possible to the background-free exposure in your experiment to maximize your sensitivity. So you basically, that's a good investment in your isotopes, because isotopes are expensive. The more isotopes you have, the better it is, but you should always basically try to be as close as background-free to make the best, to have the best discovery sensitivity. And I will come back to that later in how we did that in GERDA, and also we plan to do that in the future for LEGEND. Now, last slide before coming really to the GERD experiment. Here's just a list of isotopes which are being considered for Neutrinoless double beta decay experiments. And you see most of them, apart from tellurium 130, has a natural isotopic abundance of 34.5%. All the other ones are at the few percent level. And what is typically pursued is that you have to do isotope enrichment. Apart from tellurium 130, all other experiments rely on isotopic enrichment. For germanium 76, we are at 77.6% natural abundance, and we go up to 90% in enrichment. Here on the right side, you see Q beta beta, and that's always has two impacts. One, the higher Q beta beta, the bigger the phase space becomes. And also, if you talk about backgrounds, typically, if you go to higher energies, it's easier to reduce or to suppress background. But this is not a general rule, because obviously you can have alpha backgrounds at higher energies, and we'll discuss that for the specific case of germanium, who is rather on the lower side, which actually is the experiment which has the lowest background amongst all double beta decay experiments if you normalize it to the region of interest. Now, looking at the Nucleomatrix elements, also there, as an experimentalist, you look, is there maybe an isotope which is just superior to the other ones? And this is a compilation here from Engel Menendez, and they have also done some recent updates. But my qualitative argument is unchanged here, even though the numbers have a little bit changed. You have something about a spread order of 2 in the Nucleomatrix elements. And if you look later on the isotope, on the rate here, signal rate per 1,000 kilograms for an exposure, and you take the middle Nucleomatrix elements for 17.5 for, this is the lower number more or less for the inverted ordering, then basically you see the numbers are very small and they're not so different. So 1, 3.5, 2 number of events per 100 kilogram years for this parameter. So the choice of the isotope is mainly driven by the experimental considerations. It's not that you have one winner, which is so much clearer, stronger than the other one. And if you put in the experimental choices and efficiency things, then so it's not driven by that. That's basically the takeaway for that. So it's important to have different isotopes and probe, because obviously if one experiment comes up with a signal, you want to make sure that this is not just a wrong measurement or some confusion or some background. You definitely want to confirm, and you have several measurements, and then to pin down maybe on the long term even what the leading term is driving this Neutrinoless double beta decay. So finally, I come to germanium. And germanium is the element being used in the GERDA experiment, the Majorana experiment, and in the future LEGEND experiment. Let me just put here the key points So it's germanium decaying to a selenium with the 2 electrons with the Q beta beta at 2039 keV. High purity germanium detectors with larger than 87% can readily be produced. The concept is the source is identical to the detector. So we enrich the germanium, we transform them in germanium detectors, and then we have a very high detection efficiency. Also, the purity of this germanium is incredible high. So far, I can in GERDA we have basically not seen one bulk decay of uranium thorium chain, and can pose very strict limits on the intrinsic impurity. The high density of this material of germanium detectors leads to the fact that neutrinoless double beta decay event is point-like. The range of the electrons is of the scale of a millimeter, basically inside. So, and you have some spatial resolution with modern detectors exactly on this millimeter scale. So for us, the signature is point-like event. And last, but not least, the semiconductor detectors have the best energy resolution for large detectors in the moment, second by the cryogenic detectors of basically at the per mil level for which have maximum at Q beta beta. And showing here is just a simulation how you expect the signal to grow in. And you see here basically that's here the 2 neutrino part, and there's basically no smearing in here into our signal region given this extreme high energy resolution. Now, let me stress that the signature we call, say, it's point-like energy deposition in the detector bulk, and it's this sharp peak with an energy resolution of 2.5 keV. That's basically what we can achieve currently, and we really make use of topology information. I mean, so it's not just a colorimeter, we really make topology information, as you will see later on. So how do we discriminate, we make use of this topology? Here on the very left, you see, so this is our 2 detectors as we were using them in GERDA, the so-called P-type Beji detectors. They are basically 0.7, 0.8 kilogram heavy. And now a neutrinoless double beta decay, basically the charge cloud being point-like is drifting then along the electric field. And this, the electric field is designed such that we have kind of a funnel effect. And then basically they all run the same path at the very end and have a very similar structure. I will discuss that also in a moment. So we say these are point-like events. Now, a very simple topology is if you have a background from a gamma, which hits 2 adjacent or distant detectors, very easy to identify. But now let's look at here our, for example, interaction of a gamma, which has here 2 multi-site interactions. So you have 2 charge clouds which drift in the electric field here, and they basically, we recognize them as so-called multi-site events. And you can just think of these germanium detectors as kind of a time projection chamber in principle. I mean, you see this charge moving and you see how they induce a signal, and these signals you can basically differentiate. These are 2 charge clouds arriving at different times, and they're very powerful to discriminate. Now, we use P-type detectors. This basically means you have a lithium layer here all around, wrapped around, and this lithium is thick enough that no alpha decay on the surface can penetrate into the bulk. The only area which we're susceptible, we're sensitive to alpha events is here, this P plus contact, very thin P plus contact. If you have an alpha event here, you see a signal. However, given that here the signal is carried, is driven by the motion of the electrons, while here it's the holes which drift down here. Here it's the electrons which, and the mobility of these electrons are just much higher. And again, we have a very clear signature of alpha events decaying on this surface, and event by event, we can basically discriminate that. Now, this is all the topology inside the germanium, but in GERDA and also in LEGEND, we're using another feature, namely we operate these germanium detectors in a liquid argon volume. And this liquid argon volume serves as a coolant, but also as a detector material. And this detector material, basically liquid argon, is well known. It's a fantastic scintillator. You produce here your argon excimers, and then these excimers basically de-excite and emit 128 nanometer photons, which you can detect. And it's clear if you have an energy deposition inside a germanium here, which looks point-like a Compton scattering, for example, could look like a neutrino stop beta decay, but this escaping gamma is depositing energy in the liquid argon. You get a light flash and you recognize, and you can just basically just then discriminate that. So these are the key elements for our topology analysis of events to recognize background discriminated from signal-like events. Now, how do we implement that? In GERDA, we have here the Gird experiment located at the Gran Sasso laboratory, 3,500 meters water equivalent underground. And this, we have a large liquid argon, large water tank, 10 meters diameter roughly, which serves as an outer shield against neutrons. It's a muon veto, Cherenkov veto, and an additional passive shield against radiation from outside. Then we have located a liquid argon cryostat here inside the water tank, and that is filled with 64 cubic meter of liquid argon. And you see some additional copper layer around for reducing shield radiation from our steel. And here in the very center, we have here basically our germanium array with a light instrumentation. And we can move everything up and down here through the lock system into the cryostat, but we can also remove it and modify something. But let me now zoom into this inner part. You see here basically here our array. You see here the germanium array, and here we have a light readout in GERDA. This consisted of a so-called wavelength shifting fiber shroud, which was read out here with PMs at the top end. And then in addition, we had PMTs at the top and at the very bottom, far away from the germanium detectors. Even though they're low radioactive PMTs, we had to move them far away, otherwise the background induced by these PMTs, just the intrinsic radio impurity would have been too high. So we have to move them away, while with the liquid fiber shroud, we can get closer to the detectors. They're much cleaner in terms, and we can pick up the light very close by where it's basically produced and guide it here to our PMs. Here you see a picture of the whole device, how it looked in GERDA. Now let's look at the germanium array here, a drawing of our germanium detectors here. This is a picture of how the different strings are mounted, and you see a photo of that. Here you see the Beji string. You see also our phase 1 detectors string. And so we had a combination of different detectors used in GERDA, especially in phase 2. Now, let's look at our detectors, especially those phase 2 detectors, the Beji detectors. We mount them with a low mass holder and silicon plates, and we do a wire bonding to minimize contacts, and all materials obviously screened. And here we have our cables, high voltage and signal cables, and the electronics, the front-end electronics here in GERDA is sitting up here, and we just run cables to the detectors. There's no amplification here close by to the detectors. This was in the design we were operating in GERDA quite successful. Now, GERDA phase 2 data taking started in basically January 2016. And you can see here basically our duty cycle and the runs here. The width of these bars tells you the run time, and you can see also the exposure gain here per kilogram years and days. And you see here, so basically we ended in December 2019. We reached our design goal, which was the 100 kilogram years of phase 2. And you can see here we had some intermediate, some upgrade period where we went basically to the so-called phase 2 plus, where we added new detectors, the so-called inverted coaxial detectors, ICPC detectors, which are very similar to our Beji detectors, but much bigger. And this was also in view of LEGEND. We wanted to test new detectors which are much more massive, but have still the same discrimination power as our Bayesian detectors. So basically, we had a very high duty cycle in the 4 years of operation of about 90% duty cycle. And this is including the upgrade work. And then basically the 104 kilogram years of data selected for analysis here we achieved in the end of 2019. Now, this is a background spectrum here before any analysis cut, just very prior high level cuts. And you see that here this all added together with a large binning. And you see that we have some structure. We're not background free before the analysis cuts. At high energy, we see here polonium-210. These are these events here on the P+ contact or in the borehole of the coaxial detectors with some tailing down here, if you can see my cursor. And then you see a few features like some counts of the thallium-208, 2.6 gamma line. You see here from bismuth-214 and also from potassium-42 and potassium-40. Now, basically, we looked at our pre-update data set and made a background model on this background before analysis cut. And so you can see basically here at Q beta beta, what is our main contribution to the background before analysis cut? You see here, this is tailing of the alphas on the P+ contact. Then we have here this red line here. So basically, which is our potassium-42. And then we have here some contribution from the bismuth-214 and the thallium-208. So that's of similar orders. And this background model basically was built on the single detector data and simultaneously on two detector hits here to constrain this background model. And you can read it up here in this paper. So basically we have a good understanding of our background before analysis cuts. Now, the first step of coming back here to our full data set, we're using here our information of the pulse shape discrimination, basically making use of our intrinsic or internal topology. So shown what I was discussing here in this part. And you see now here for the alpha background, this basically completely disappears. There's one caveat, this is the full data set including our coaxial detectors. And there's some alpha stay over deliberately in this, just for coming from this coaxial detectors. If we're looking at the Bayesian detectors or the IC, the new detectors, they are basically just free of even alpha background. Now, you see here at Q beta beta, we still do have some events. And now the next step is basically to look at our liquid argon signal. But maybe before, I mean, our method in how to discriminate our parameters is what we call the monoparametric A over E cut for the Bayesian and the ICPC detectors here. And for the coaxial detectors, we do some artificial neural network analysis plus some consecutive rise time cut. And we train our data here with calibration data. And we can check our significance, our signal acceptance really from our two neutrino data. And we tuned basically our analysis cut such that we have a signal acceptance of 90% for our Bayesian detectors, and for the coaxial detectors only 70%, because there we have to, this, let's say, old style of detectors, we have to cut harder. But let's say also for the future, that's basically you have very powerful method to tune your acceptance cut. Yeah, first, before we apply our liquid argon V2, we just do the opposite. We make liquid argon coincidence just to see whether what you can use that spectrum to understand background much better. For example, if you look here at the potassium-42, you see a beautiful Compton spectrum here with a Compton edge. The same here, if you look at the thallium events, you can basically reconstruct also here the Compton spectrum here for the thallium. So that's basically in coincidence events in the germanium in coincidence with the liquid argon signal. So Now, you can also ask, what is the random coincidence or is our signal efficiency? So basically, the signal efficiency is limited by dark rate and argon 39 rate, and it is larger than 97%. So basically, we tuned the system such that our random coincidences are so low that it's less than a few percent. So we hardly lose any signal, good signal we're searching for with our liquid argon system. Now, here comes now the spectrum after we do the anti-coincidence. So basically, we have done our pulse shape discrimination. This was the gray one. And now after the liquid argon, basically here, there's only very spare single counts at Q beta beta or above. And if I mentioned it before, if we were looking only at the Bayesian and the ICP detectors here, basically there's no events here at higher energies left over from the alphas. Now we can zoom a little bit into the details around Q beta beta. And just a reminder, we always were doing a blind analysis. From the very beginning in GERDA, we always had a rigorous blindness scheme in which we basically did not open until all the cuts were fixed and finalized, and then only in the very last moment, then we basically opened this box and looked basically at the counts and the numbers which we had there. So this is what we call here the analysis window, and you see here basically the distribution here of 13 events here in this region, and the closest event here is something like 2.5 sigmas away from our Q beta beta. And you can also now determine the background index, what we have observed. And this background index is something like 5.2 times 10 to the minus 4 counts per kV kilogram of year, with an energy resolution of now for all detectors here together of 3 kV, full half maximum. So basically, you can see that we're in this exposure of 100 kilogram year, excuse me, we have less than a count expected in the window. So for the final analysis, we made an unbinned maximum likelihood fit. We did some data partitions. We use our phase 1 data and fitting then the whole data, basically a Gaussian signal on flat, basically on flat background for this different data partition. The fit reports as the best strong signal, basically 0 signal events. And then if you use a frequentist analysis, then this then translates into a half-life limit of 1.8 times 10 to the 26 years. And in this case, the median sensitivity basically is just gives the same value by coincidence, as you will see also in a moment. We always did also a Bayesian analysis with different priors, and just for completeness, they're given here for flat priors here on the rate, or if you have a flat prior on beta beta, you get here these numbers here for the 90% confidence intervals. So the official number, which is quoted by GERD, is always the frequentist numbers, but we also give the other numbers for information. So now you can take here these GERDA numbers, the final numbers, and plot them here again as a function in beta of your lightest neutrino mass, and that's basically here the blue band. And you give here, and the width is given here by the Nucleomatrix element uncertainty. And so we end up with something like 0.08 to 0.18 electron volts. So that's the parameter range here given by Nucleomatrix elements. And you can compare it to the our competitor experiments, Camlanzen or Quore, which have currently basically these limits on in beta beta. The windows are quite wider. If you look, that's basically the reason it's coming from the uncertainties of the Nucleomatrix elements, which is basically a bit wider for the xenon and for the tellurium backgrounds. Let me show you here just one other presentation. You can obviously also plot here in beta versus sigma, basically from your cosmology observable. And you know that here from cosmology, the numbers are depending a little bit on whether you have the minimal model of 0.12 electron volt. And you can also plot it here against M beta. So the direct measurement from Katzin experiment is about here the 1 electron volt scale. And now you can also think about whether you can transform here your M beta on this other parameter under the assumption that neutrinos are Majorana particles. And you can basically derive here on the light neutrino mass, well, or on the sum sigma or on M beta beta, basically this parameter. So you say, but obviously these are not independent. This is always under the assumption that, for example, here that neutrinos are Majorana particles. Now, let me summarize here the GERDA part and give you then the outlook for LEGEND. So I think, so GERDA started, had always the goal to operate quasi-background free. And I think, so we said we always have to improve our background once we increase our exposure, and we successfully did so over the years. So with the first result of GERDA phase 1 here, 2013, and you see always the black circle is the median sensitivity, and red is the limit. And you see here that sometimes our limit is stronger than our sensitivity, or vice versa. For example, 2019 here, our median sensitivity was stronger than our limit, and just here basically with the last measurement, our sensitivity and the limit is just by accident basically coinciding. So, but important is you see here basically our sensitivity or our limit is scaling on this linear line, which is basically the background free scaling. And that's what we want to continue here with LEGEND for in the future. So now let me briefly introduce you to LEGEND. So far I spoke about GERDA, but we are not alone. Luckily, we had a friendly competitor, and we always had the plan that Majorana and GERDA, beyond when finishing their experiments, that we go together and build a joint experiment, which we now call LEGEND. And we combine basically the best of both, and basically you will see that lots of the technologies from both sides are basically being implemented, and we're convinced that this is really then makes the difference to continue with a large mass and low background. So here you see the LEGEND collaboration with the photo here. Before we all went to virtual meetings, so we are something like a bit more than 200 collaborators from roughly 50 institutions worldwide. And we basically decided that we want to develop together a phased germanium-76 based double beta decay experiment program, and with a discovery potential, the half-life beyond 10 to the 20 years. And we want to use existing resources as appropriate to expedite physics results. So we really want to go phased, fast, and do physics all the time. So the first step in that direction is LEGEND 200. And LEGEND 200 will operate up to 200 kilograms of ICPC, this new detectors, BEDG and PPC. We basically pulled together all the detectors which we have, plus implement a lot of new detectors which are currently under production. And then we want to reduce basically the background in this kind only by a factor, roughly 3 to go below 2 times 10 to minus 4. Just remember in GERDA, we're 5 times 10 to minus 4. So that's not a major improvement. So just we talk about a factor of 3 reduction. And we want to have a half-life sensitivity of 10 to the 27 years. So 1 order of magnitude. And this is going to be operated at Cansasso. And we want to start with this experiment this year. And we're in phase of intense construction work despite the COVID pandemic. In parallel, we're preparing for the next stage, LEGEND 1000, which then operates up to 1,000 kilogram. And this will be basically in payloads of individual loads of something like 250 kilograms. And again, we want to reduce the background further to 10 to minus 5 counts to be able to reach a discovery sensitivity of 10 to the 28 years. And where this experiment will be located has to be still selected. The 2 contenders is SNOWLAB and Cansasso. And when it will take place depends very much on the funding decisions and the timing of the funding. What are the key technologies for LEGEND? LEGEND, we want to use large mass high purity domain detectors, which are inverted coaxial detectors, so Beji type of detectors, but larger. And the original idea is from David Radford and his collaborators and published here. And active masses up to 3 kilograms we want to achieve. And the PSD we've shown in various detectors in the meantime that these are really excellent, as good as with these Beji detectors. We also want to improve our liquid argon scintillation readout, because in GERDA, we used a liquid argon, which was reasonable, but it was not optimized we had in terms of primary light, attenuation lengths, and many other features. And for LEGEND 1000, we in addition want to get rid of one background just by avoiding it at all. We want to use basically underground liquid argon, which is depleted in argon 42. And so basically one key background we could then basically just avoid at all. So material selection is an important process, and we're constantly improving radiopurity. And here the Majorana collaboration has done major efforts in the past with electroformed copper being produced underground. And that is basically for the small parts close by basically will be used. And then we will use here also new optically active material. We want to minimize passive material as much as possible. And this PEN material as a structural material is also, it's a wavelength shifter, it's a scintillator. And again, it's like the liquid argon, you have energy deposition in there, you get a scintillation light, you can recognize this was a background. So also we want to enhance active background rejection, for example, for muon-induced backgrounds. And this is especially important for if the site was Cansasso and not SNOLAB, because SNOLAB, you're deeper and you have very much, basically you don't have to worry about muon-induced isotopes. At a more shallow depth at Cansasso, then this is surely something you have to worry about and you have to study very carefully. So let me here give you an overview of our background projections. This is still work in progress, and we're working on the PCDR, and numbers are still a little bit afloat, but you can see here in this scale where we are for LEGEND 200 and where we want to go for LEGEND 1000, and that's all based on now material screening, modeling, and you see that here for LEGEND 200, our goal is set less than 2 × 10⁻⁴. And our background model tells us that with the material which we're using, we should be below there. We have even some margin. And you can see that we are, let's say here, the liquid argon 42 is an important contribution for background and the near components. Now, if we want to go to LEGEND 1000 as a next step, you see here the dark blue scale here on the logarithmic scale, easier to see. And you see here, important here is the argon 42 reduction here by using underground argon. If you go to SNOLAB, then you're here, you get rid of the muon-induced completely. For Cansasso, you have to work hard to get it here low enough. And there are obviously some other contribution. And you see here, that's basically our background model with some uncertainties. The gray line part is the uncertainties. That's where we want to go. And as just to remind, it's still preliminary, these numbers, they will still change a little bit before we come out with the final PCDR. Now, here to give you an overview of our overall program, I showed you here this discovery sensitivity curve. This was the background free, the solid line, the background free line. That's here our background. We're aiming for LEGEND 1000. And you see here basically the exposure and the sensitivity, discovery sensitivity we have achieved here with GERDA and Majorana. Now here with 1 ton exposure, years we will have LEGEND with 10⁻27, and then here with a bit more than 10 ton year exposure, then we will basically here be sensitive here for our beyond the 10⁻28. So here again, the key parameters which we're aiming for background index at the 1 or 2 times 10 to minus 5, and an exposure here then beyond the 10 ton years. Yeah, a few. I'm looking at the watch, and I should come also to an end. I see it, but just a couple of slides here. The underground studies, which are ongoing for SNOLAB, there's a very close cooperation with SNOLAB to work out basically here the design in the cryopit. And you can see here the cryostat with the 4 payloads. And you saw also what we call insertion tubes, which basically will hold then the underground argon, while the other part is filled with atmospheric argon. That's basically here our design we're working on. We're also studying here for Gran Sasso some configurations. Here, this would be, for example, repurposing the Borexino outer watered tank and locating the cryostat inside. And here, this is the generic design study of the cryostat for under seismic events at Gran Sasso, but obviously here for SNOLAB, and that's basically here the internal part, which is obviously independent of the location. So let me say something here about our timeline, what we're thinking about. Legend 200 is basically in preparation for this year. We will start with liquid argon filling, hopefully in a few weeks from now. And then we'll have then in early summer, the first strings being commissioned. And we'll use this year here for commissioning and start then with physics run as soon as possible. Obviously, COVID is also slowing us down somewhat and making life a little bit more difficult, but we are still positive that we can do that this still year. Now, for Legend 1000, critical time scale is we expect this year. There's kind of portfolio review organized by the DOE. In the past it was called down select. This is now scheduled for for the summer, early summer. Most likely dates are not yet completely fixed. And then our goal is that we can really build within 5 years the infrastructure and start with the first payload after 5 years, while still detectors are being produced and the next payloads can basically add, and so we can really start. Obviously, these timelines are contingent on the funding decisions. We are working hard to have aligned on the that's on your side of the Atlantic, and also on the European side to get basically everything set up. So here, just some key parameters again, which will end up in our PCDR, our discovery sensitivity for limit setting and for discovery. So for the signal discovery, it's between 10 and 21 milli-electron volt, depending on the nuclear physics matrix elements here given here. Now, publications on Legend 1000 are still, let's say, a little bit scarce. We've worked hard to get the experiment going, Legend 200. However, we have here in the SNOMAS process, some letter of interest shown, and also here discuss the application of underground argon here together with the argon underground community, central around deep and dark side. And there's also a paper on the on BSM searches. Most important, our PCDR is under preparation and will basically be published soon. However, coordinated with the down select portfolio review in this early summer. So we'll come out with that basically sometime before that meeting. Let me have one before the last slide, just putting everything on one plot. Sensitivity and the so-called sensitive exposure versus sensitive background. And that's basically, by Matteo Agostini, Jason Detfire, and Giovanni. They basically worked on that plot to compare experiments. And sensitive exposure is always correct for your signal acceptance, And obviously your background, you have to also consider your signal acceptance, because if you cut too hard, then it's difficult to compare. And you see here basically then the lines here, this is the half-life 10 to the 28 year, and that's the goal here for Legend. That's basically where GERDA is in the moment here for Legend 200. We want to get here, and you see, so we try to be here on this line, which is basically here always staying background free. And these are, for comparison, are the other experiments, which are also making great progress and moving forward. And we look forward to have really, I mean, timely different isotopes trying to explore this really interesting parameter space. Now, that's my last slide, and I will really stop after that. In my summary, I think we can say that Legend really builds on the successful GERDA and Majorana experience. In this talk, I've discussed lengthily the GERDA experience because that's also my background, but this should not mean that the Majorana experience is less important for making Legend a success. So these are the two key pillars, and we have also new groups who have basically joined and really are bringing in very important expertise to make Legend a success. And to repeat, we follow a staged approach, and we have a discovery potential at every stage. So it's not that Legend 200 has no discovery potential. We're really in each stage, we are basically ready for seeing a signal. We consider Legend 200 as a major asset for our Legend 1000 project, because what we're doing in Legend 200 is we're testing already components, very much those we want to use also for Legend 1000. Moreover, I mean, you know, we get very detailed experience on the costing, on the schedule, and it is for the collaboration built on Majorana and GERDA and all the new groups, and a fantastic exercise basically to work together. I mentioned various times that we are preparing here for this portfolio review, assuming summer 2021. And we are preparing to get all that done in parallel to the commissioning of Legend 200. And I think it's fair to say that Snow Lab and LNGS offer unique underground locations to realize Legend 1000. And I really look forward to work at either of these two places to realize Legend 1000. So I'm sorry that I took a little bit longer than planned, and happy to end here. Thank you very much.
Thank you very much, Stefan. Sorry for the clapping. So are there any questions? Yes, Chris, go ahead.
First of all, thanks very much for a terrific and comprehensive talk. There was a slide marked slide 10 in which you showed the zoom in on the background region for the most recent GERDA results. Mm-hmm. Yeah, that's the one. So this slide puzzled me a little bit, because the green line seems to be interpreted as a constant background over that entire analysis window, whereas all the events seem to be in the left-hand side of it. So couldn't a skeptic say that that green line should be twice as high?
You can think about that it's maybe tilted and has a slope.
Sure.
So yes. So I mean, we were looking at that, whether we have kind of a statistical indication that this is not equally distributed, and there's no strong indication if you look at it, and you can also infer from your background expectations from the background model. I mean, I've shown the background model before analysis cut, and I did not show you now the background model after, because we don't have that really ready, but we're working on that. So we have obviously for the different isotopes PDFs, how they should look like, and also that basically rather tells us it should be flat. And also if there's a slight slope, the uncertainty, let's say the sensitivity is not really changing.
Thank you.
But yeah. I mean, it's important, you know, the definition of this background index we fixed beforehand in the definition, we don't do that, and we always kept that always the same over all the years in the different analysis, such that you really can compare it.
Nigel, you're next. If Chris has finished.
I am. Thanks very much.
Okay.
Sorry, my hand's still up, isn't it?
Yeah, that's why I was confused. Okay, thanks. Go, Nigel. Sorry.
Hi, Stefan. Thanks for a great talk. So on your slide 16, you have cosmogenics of the germanium as one of the backgrounds that has quite a lot of impact, and there is a shift between legend, small shift between legend 200 and legend 1000. Is that just a limitation of the processing time on the surface, or are you looking at doing anything dramatic like reworking the detectors underground?
You mean here this germanium cosmogenics, this two here? Yeah, it's just basically the longer measurement time that, so it's the germanium 68 which just decays away. Okay. So so moreover, I mean, our set, the planning is really, I mean, we're doing germanium detector production always above ground with the intermediate storage. So we try obviously to optimize, to learn from our GERDA, Majorana, now LEGEND experiments to reduce our processing. And moreover, we're also thinking that our pulse shape analysis also gets a bit better. So there are various little changes for the germanium 68 here.
Okay, thank you.
Are there any other questions? Since we are still on this slide, the goals in blue, dark blue on the right, does consider the LNGS or SNOLAB muon induced?
So the goals is, we must meet the goal. If we don't meet the goal, we make something wrong. So if Granzasso was the lab, we have to, I think we're still here on the little bit on the high side. But I mean, that's the goal we said we want to reach below the 10 to minus 5.
Yeah, but and the bar and the blue bar below, it's considering the LNGS and the SNOLAB, no, LNGS, the conservative one, right?
That's a conservative one. Okay. Yeah. But please, I mean, this still preliminary, these numbers, they're a little bit moving up and down.
Okay.
Down, hopefully more than up.
We have another question from Jeter.
Hi, Stefan. Thank you for the talk. So I guess I had a question for you on the future of the technology. So let's look past Legend 1000, and are there ideas of how you could get down to that milli eV scale or below?
Yeah, good. So I mean, in this APEC report, we were discussing this roadmap, discussing also, is there a kind of a no-go theorem for one or the other technology? So, in principle, we don't see a reason that one could not further increase, apart that maybe things get unaffordable or very challenging. In the moment, nobody really dares to make a statement that you can get down with the technology, with a known technology, down to the normal ordering bottom line. So, I would not dare in the moment to advertise to go ahead with germanium for that, but with none of the technologies in the moment is ready to make such a statement, even though some people do make statements like that.
What are the biggest issues preventing you from making a statement like that?
The experience is you have to improve background. So now, I mean, if you have to go down from 10 to minus 5, you have to get another order or down, and you come in a region which it's very difficult to make any predictions on that level. I think you know, in GERDA, we learned obviously that our main backgrounds we were thinking to be our main backgrounds were not our main backgrounds. So I think going a factor of 10 in background reduction is a big step. And I think then you have to measure that background and analyze it and understand it. Then you can make the prediction how you can continue to do the next order of magnitude.
Okay, so you want to run Legend 1000 and see how close you are with these histograms.
Well, you know, I think first of all, there's a fantastic discovery potential over the year to come. So if we don't see a signal, then obviously you want to continue to do the next round, and then you have to see what is the right method to come up with a competitive experiment. Whether this is then germanium or something else, I think we have to see then.
That's true. The counts in the region could be signal. That's a good point. Thank you.
So Art as a question.
Very nice talk, Stefan. I have is there a combination of results from cosmology and double beta decay that would enable you to state whether neutrinos are Majorana or not?
So from cosmology, I mean, in principle, there's a guaranteed signal if you have the 60 milli-electron volts for sigma. I mean, should be visible at some point. So within now, your question is, I think so? If we see a signal in cosmology at this level, and you don't see a signal in double beta decay with the right sensitivity. Now I'm just trying to, or maybe I had this on the logarithmic scale, this plot down here. You could probably at some level start to rule out Majorana neutrinos. I think, you know, not seeing it and seeing a clear signal is cosmology at a higher level. Let's say if the level would point to the inverted ordering, and the double beta decay does not see a signal and being sensitive to the inverted ordering, then I think one could rule out Majorana neutrinos, or I'm sure there's some other caveats people can come up then with. But I think this would point then probably to Dirac neutrinos.
Probably has to be the inverted hierarchy in order to do something definitive in a finite period of time.
Yes, I mean, we hope that Juno and the long baseline experiments can tell us then until what the ordering is, and then obviously we can close down on the hypothesis variations.
Yeah, okay, thank you. Very nice talk.
Thank you.
Are there any other questions? At some point I saw Chris' hands up again, but maybe I was mistaken. So if no other question, I would like to thank Stefan again. Thank you very much. And yes, thank you very much, and talk to you next time.
Thank you very much. It was a pleasure to see you all. You know, I feel quite home sometimes after many years of SNOLAB EAC. I hope you had a good EAC recently.
Yes, we did. Thank you. And Bernhard is a good addition, so thank you for that recommendation.
Good that you could convince him. I'm very happy. Okay, thank you very much.
Thanks, Stefan.
Thanks a lot. Ciao.
Goodbye.
Nice to talk science and not reviewing things, actually.
Yeah. Okay, bye-bye.